I don't know, somewhere in the church case. I don't have it.
Port St. Lucie.
Port St. Lucie.
This other 1 hour from the house, and if not let me right.
Okay, we're on the air. So to begin with, any questions? The midterm is a week from Thursday. So the plan is this. First of all, there's a sample midterm exam that's posted on the website now. So you can download that, and I'm going to discuss that in class on Thursday. So you should take that as the way to study for the midterm. And Tuesday, well, that depends on what happens on Thursday. And also Thursday, I tend to hand back homework 0 and go over it in class. The exam will cover everything up through Chapter 3, all the stuff we've done. The stuff when I start on Chapter 4, which I may do on Tuesday, will not be on the midterm. So last time we were talking about the case where we sampled and we asked the question, what's the probability that one event occurs before another? And I wanted to apply that to the craps problem, which I discussed briefly. So everybody up to date? Okay, don't forget, go to the website, download the sample exam, which is the midterm from the previous semester, summer, and use that. Well, first of all, you should try and do that prior to the lecture on Thursday, because as usual, if I do it in class without your having thought about it, it's all going to look a lot easier than if you try and do it first. Also, if you try and do it and get nowhere, and then you see an explanation, you'll learn a lot more than if you simply wait to see the explanation, because it goes in one eye and out the other. Okay, so no questions, right? So, we were talking about the question where we had a sample space, and we could partition it into 3 pieces, say A, B, and C. We're interested in A and B, and C is just everything else. And the question was, we're going to sample from this sample space. We're going to conduct this experiment as many times as necessary until either A or B occurs. And the possibilities, since this is a partition here, are in any trial you get either A or B or C. And the question is, what we'll call P is what's the probability that we get A before B. And in the textbook, the author made the assumption that these were independent trials, and then he calculated this probability by assuming that the sequence of trials could be factored in a sense, because they were independent into the product of the probabilities on the individual tosses or individual trials. And then he used a geometric series to sum things up, and he got a formula. And then I observed that the formula was correct whether you had independent trials or not. Because what the question is being asked is this. The P, right here, the probability of A before B, is the probability that I'm going to get A, given that the resulting, the final trial is either A or B, because if it's not, then we simply repeat the process. And it doesn't make any difference when I apply this conditional probability formula whether the trials are independent or identically distributed or anything. I'll just write the formula. If I know that on the final trial I had to have either A or B, and I asked for the probability that in fact it was A, then by the formula for conditional probability, the denominator is the probability of the event which I'm conditioning, which is the probability of that union. And since these events are mutually exclusive, the probability of the union is the sum of the probabilities. And the numerator is the probability of the intersection of A with the event or the union A or B. And obviously that's exactly the same as A, so the numerator is the probability of A. And this is exactly the formula that the author derived, assuming that the trials were independent, but I haven't made any assumption now about independence. So now I want to use that in the for this craps problem. So let me define craps. Okay, so this is a dice game. And this is a standard problem in lots of textbooks. The reason I like it is because it kind of puts together lots of things that we've done in this chapter. Unfortunately, this particular problem is not in this textbook, so I'll have to state it and write it on the board here. But here are the rules. You roll 2 regular dice, ordinary dice. The value of the roll, of course, is the sum of the 2 dice. And if on the initial roll, which I'll call x0, you get either 7 or 11, you win. If you get 2, 3, or 12, you lose. If you get anything else, that something else is called your point. And then you continue to roll the dice until either you get your point or you get a 7. If you get the point first, you win. If you get the 7 first, you lose. That's the game of craps. So whether you win or lose depends on what you get on the initial roll, in part, and also the number of trials, number of rolls before the game ends is not bounded. There's no maximum number of trials before the game is required to end. So you have, in that sense, an infinite sample space. And the trick, of course, is to reduce it to a question about probabilities associated with the single roll of the dice. So now, well, let me write out what the rules are first. Okay, so what I'm going to do here is, here's my definition. I'm going to let x0 equal the value of the initial roll. The initial meaning the 0. And I'll let, and then, the way it works is this. If x0 is an element of the set, or is one of these values, 7 or 11, then you win. If the initial roll is an element of, shouldn't say equals there, if the initial roll belongs to the set 2, 3, or 12, then you lose. If x0 is anything else, which means 4, 5, 6, 8, 9, 10, then that value is called the point, P-O-I-N-T. And then, finally, write it here, if game does not end on initial roll, in other words, if you don't get either 7 or 11 or 2, 3, or 12, that means you must have had something else which is called the point. Then roll dice repeatedly until get either 7 or point. And then, if you get the point, then you win. And if you get the 7, then you lose. Okay, so is that, can you see that? Is that clear enough? Let me repeat it if it's hard to read from the board. You roll 2 dice. Your initial roll, which I'm calling x0, if it's 7 or 11, the game is over, you've won. If it's 2, 3, or 12, the game is over, you've lost. If it's anything else, that is 4, 5, 6, 8, 9, or 10, then the game continues, And that value that you got is called your point. And then, if the game is not ended, you roll the dice repeatedly until either you get a 7 or you get your point. If you get the point first, you win. If you get the 7 first, you lose. And the question is, what's the probability of winning? Okay? So, let me define this as this way. Let W stand for win. So W is the event that I win. X0 is the value of the initial roll, which is the point, or at least it's the point if the game hasn't ended. And let X be the value of an arbitrary roll. And you want to calculate the probability that the player wins. So the first observation is that the way to look at this is obviously to use the theorem of total probability, because you can see that you have a partition of the sample space based on the initial roll. Either you got 2, 3, 4, 5, 6, or so forth. Under each condition, you want to calculate the probability that, given that the initial roll was such and such, that the player wins the game. So I can immediately write it like this. This would be the probability that the initial roll takes the value I times the probability that the player wins given that the initial roll is I, summed over all I, which are the numbers here between 2 and 12. So this is total probability. So this is one of those examples where it's obvious that that's the way to solve the problem. And now all I got to do is fill in the stuff on the right-hand side. Okay, so some of these are easy. In fact, they're all easy. What's the probability that I win given the initial roll is a 2? Of course, that's the same as the probability of winning if the initial roll is a 3, and the same as the probability of winning if the initial roll is a 12. Because by definition of the game, you lose. That's right over here. On the other hand, the probability of winning, if the initial roll is a 7, is equal to the probability of winning if the initial roll is 11, and that's 1. Okay, so the key question then is, what are the others? For I something else, that is, I either 4, 5, 6, 8, 9, or 10, the question is, what's the probability of winning ultimately if X0, the initial roll, is I, where I is not something that either loses or wins the game, but is what we're going to call the point. So that's the same thing as asking, if I'm going to roll these dice continually until either I get an I or I get a 7, what's the probability that on an arbitrary roll, X, I get the value I, given that I know that X is either equal to I or X is equal to 7. Okay, so the key here is to recognize that I'm going to roll the dice continually until I get either something or something else. And so this is exactly in the same framework as what we wrote over here. Now notice that this given sign, this is given that initially I'm going to get this value I. But now what's going to happen is now I'm not on the initial roll anymore. Now what I'm simply doing is saying, okay, we've set this value I, that's the point, and the question is, I'm going to roll these two dice until either I make my point or I roll a 7. What's the probability that the point comes first? So according to the analysis that we just made, that would be equal to the probability that on an arbitrary toss of the dice, I just take the two dice, I roll them, what's the probability that I will get this particular value, given that I must get either that or that? Because if I don't, I ignore the roll, I ignore it, and I do it again. So we already know what that is. And that value then is the probability that on an arbitrary or ordinary roll, I would get I, divided by the probability that I get I, plus the probability that I get 7. Okay, so this is my formula right here. And I'll go back and use it over here. So notice that by making this observation, I've simplified things. I don't have to worry about how long the game is going to go. In fact, I don't even have the requirement that the tosses be independent, even though you would presume that they are here because we're just rolling two dice. Okay, so now, what's the probability of winning? The probability of winning is equal to, now I'm going into this formula, and I'm just going to plug in the values. So when I is equal to 2, then of course I lose. So in the cases where I is equal to 2, 3, or 12, this is replaced by 0, so those terms don't appear. And when I is equal to 7 or 11, this term is replaced by 1, so I can take those terms out. So the first thing I'm going to get is the probability on the initial roll, I get a 7, plus the probability that on the initial roll, I get an 11. And then I have all the other terms, which are the sum for all other values of I. So I'll write for I in the set 4, 5, 6, 8, 9, 10. Those are all the points. The probability that the initial roll is I, times the conditional probability that now if I roll the dice repeatedly that I will get an I before I get a 7, which as we've just said is the probability that on an arbitrary roll I get I, divided by the probability that on an arbitrary roll I get I, plus the probability that on an arbitrary roll I get 7. This formula here is exactly this formula here. And now all I have to do is plug into that and I'm done. Okay, let me erase this stuff here. Okay, so now this becomes fairly simple. Equals. Okay, what's the probability that I roll a 7 on the initial roll, and we've done this 1,000 times. Just count the points in the sample space. There are 6 ways I can roll a 7 out of 36, so that would be 6 over 36. What's the probability I roll an 11? Well, there are 2 ways I can roll an 11. That's 2 over 36. Plus. And now I have to sum up all the other stuff. Okay, so let's do that. First of all, what's the probability that I roll a 4? And the probability of rolling a 4 is 3 over 36. And I have to multiply that by the probability that on an arbitrary roll, I roll a 4 divided by the probability of 4 plus the probability of 7. Okay, so the probability of 4 is 3 over 36. The probability of 4 is 3 over 36. The probability of 7 is 6 over 36. Okay, so this corresponds to the term when I is equal to 4. How about when I is equal to 5? Okay, what's the probability of initially rolling a 5? It's 4 over 36. Multiply that by this corresponding ratio. It would be 4 over 36 divided by 4 over 36 plus 6 over 36. Okay, that takes care of 5. What about 6? For 6, the probability of rolling a 6 is 5 over 36. And then the ratio is 5 over 36 divided by 5 over 36 plus 6 over 36. Okay, so this takes care of 4, 5, and 6. Then I've got to do 8, 9, and 10. But the probability of rolling an 8 is exactly the same as the probability of rolling a 6. So for 8, I add in this term again. For 9, I add in this term again. And for 10, I add in this term again. So all I'm really doing is multiplying this whole thing by 2. And the rest of it is arithmetic. So 6 plus 2 is 8 over 36. And then I have 2 times, and now it's easy. Here I have 3 over 36. Let's see, put this thing here like that. 3 over 36 times, here the 36's cancel, and I get 3 ninths. Plus 4 over 36, that's that term. Again, the 36's cancel, and I get 4 tenths. Plus 5 over 36 times 5 tenths, 5 elevenths. 5 plus 6 is 11. And then I just do that arithmetic, and it turns out to be equal to, if you work it out, exactly 2 ninths, 836, plus all this stuff here turns out to be exactly the same as 134 divided by 495. And you can put that over a common denominator. It turns out that that answer is 244 over 495, which is equal to 0.49, and then you have 29, 29, 29, which repeats forever, so I'll put a bar over the 29. So in other words, just slightly less than 50% is the probability that the player will win the game. So this looks something that looks like a very difficult problem initially, but now you see that when you put together all the stuff we have in this chapter, that it's actually straightforward. Okay, so let's go over this strategy here. The strategy is that when I play this game, whether I win or not depends to some extent on what happened on the initial roll. And so that's obviously a partition of the sample space, because the initial roll can be any one of the 11 possible values I get when I roll the dice. So I say that the probability that I win is the probability that on the initial roll I get any particular value times the probability that I win if I got that value, summed over all possible values. And then I recognize that for the particular initial values of 2, 3, and 12, this probability is 0 because I already lose. And if it's 7 or 11, it's 1 because I already win. And all I have to worry about is the other cases, which are what's called the point. Okay, now, if in fact the game is not ended on the initial roll, then this reduces to the earlier problem where we simply conduct an experiment in which there are 3 mutually exclusive and exhaustive possibilities, which are either I get event A, or I get event B, or I get event C. And the question is, I'm going to do this until I get either A or B. What's the probability of A first? That is, if my point is 4, I'm going to roll the dice until I get either a 4 or 7. And the question is, what's the probability that the 4 comes first? If my point is 5, then I'm going to roll the dice continually until either I get 5 or 7. And the question is, what's the probability that the 5 comes first? And so on. So I recognize that each of those is of the same format. And that's to say that the probability of winning, given that my initial point is I, is equal to this conditional probability, because what it says is that if I get anything other than I or 7, I ignore it. So it doesn't matter whether the trials are dependent or independent. I throw them out, and all that matters is that eventually the game ends, and when it ends, it either ends with an I or a 7. Knowing that, what's the probability that in fact it ends with I? So I plug in the definition of conditional probability, or if the trials are independent, I can use the derivation given in the textbook, but of course it gives the same result, and I get this answer right here. And then the rest of it is just plugging those numbers then back into the total probability formula and doing some arithmetic, and in this case it turns out that the answer is just slightly less than 50%. Okay, any questions on that? Straightforward? So you can see this is a very difficult problem from the viewpoint of the beginning of the course. Right? The beginning of the chapter, if I told you after you had to do this, nobody would have a clue. So what you have to do is be systematic. There's only a few basic rules here. Okay, so let me change the problem slightly. So now I want to introduce a new game, which I'll call card craps. And card craps is just like regular craps, except that instead of using dice, I'm going to use cards. So let's see how that goes. So I'm just making this one up. This was a test problem on one midterm. Maybe it was too hard, I don't know. But whether a problem is hard or easy on the midterm, you can't tell from just looking at the problem, because you have to look at what was discussed in class. And so if I emphasize that prior to the midterm, then it's no big deal, especially since the midterm, remember, is open book, open notes. And if I said to the class, okay, what I'm going to do is I'm going to give you a version of the craps game, but I'm going to use cards. That'd be a reasonable thing for me to say. Then everybody's supposed to have thought about that. And then you go home and you make whatever notes you want. Of course, you're not going to guess exactly what I'm going to ask, but it's not like seeing the problem for the first time. So maybe the problem isn't as hard as a test problem as it looks. Okay, so here's card craps. So this is my definition. So what I'm going to do is I'm going to let ace count as 7. And king count as 11. Okay, so then, as before, now what I'm doing is I'm going to pick from the cards. Now you notice that cards have denominations. So the denominations of cards are 1 through king, which is 1 through 13, whereas the dice is 2 through 12. So by making the ace count as a 7, I've eliminated the 1, and by making the king count as 11, I've eliminated the 13. So now the values that I get when I deal out the cards are exactly the same numbers as the values I get when I roll the dice, but the probabilities are different because I'm getting them from a deck of cards rather than getting them from rolling the dice. But otherwise, it's basically the same question. There's another question, and is, there are 2 ways that I can play the game. One is I can mimic the dice game in which the trials are independent, which means that with the cards I would replace the cards in the deck. So what I would do is I would shuffle the cards, and then I would deal out a card that would correspond to rolling the dice. Then I would put that card back in the deck, and I'd shuffle it, and I would pick out another card, and so forth. So that would exactly mimic the dice game, except that the probabilities on each trial would be different, but nevertheless the rules would be the same, and the independence would be the same. The other possibility, which makes more sense from a deck of cards, is I shuffle the cards, so I have a random permutation, and then I deal out the first card, that's the 0th roll, and then the second card, and then the third card, and so forth. So I would do it without replacement. So,
What would the jack?
What was that?
Jack. What would it be?
The jack would be an 11.
So we have
Yes. Well, actually, you have 8 11s. Okay, so that's why the probabilities change, but the numbers are exactly the same. So in the case in which I sample with replacement, that is, I put the card back in the deck, it's almost exactly the same. Okay, so let's say that A means with replacement, and B means without replacement. So let me calculate the probability, I'll call it, let's see, probability of winning. If I play card craps, but I sample with replacement. So this should be easy. Let's see, first of all, it's the probability that my initial roll is a 7, plus the probability that my initial roll is an 11, plus the sum of the probability that the initial roll is I, times the probability, this is now a conditional probability, that the final roll is I, given that the final roll must either be I or must be 7. This is exactly the same as before, and of course this sum now runs over the values. This is for I in the set 4, 5, 6, 8, 9, 10. And let me erase the A here, because this is true whether I'm sampling with replacement or without replacement. The only thing that's going to differ is the stuff I'm going to put in the formula. Because we know that if we sample without replacement, the same formula holds even though the trials are dependent if I sample without replacement and independent if I sample with replacement. Because if I sample without replacement, once I pick the card out of the deck, it's gone, and that's the end of it. It can't be repeated. But if I sample with replacement, then when I pick a card out of the deck, I put it back, and so it can be repeated. Okay, so let's do it under A. What's the probability of winning under A? So what's the probability of rolling a 7 if I'm playing card craps initially? So that means that 7 is the probability that when I pick a card out of the deck the first time, that the value that I get is a 7, and I have altogether 8 7s in the deck, because I have the original 4 7s, plus I have the 4 aces, because I'm counting an ace as a 7. So the probability is 8 over 52. That's the probability of rolling a 7. What's the probability of rolling an 11? Well, that's also 8 over 52, because I have 8 11s, namely the original jacks plus the 4 kings. And then I have the other stuff. Okay, what's the other stuff? Well, let's see. First of all, what's the probability that on the initial trial, that is when I deal the first card from the deck, that I get a 4? And the answer is, well, it's the same as for 5, 6, and so forth. All of those are 4 over 52.
Excuse me, what is a queen counter? What do you call a queen?
A queen is a 12. Remember that with cards, let's go back to cards. Cards we have, let me write this out here. Okay, for card craps we have, cards you have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Okay, now the ace is going to count as a 7. All these guys are going to be exactly the same. The jack is going to be an 11. The queen is going to be 12, so let me write that. Jack is 11, queen is 12, and the king will be an 11. So therefore, there are 8 7s, and there are 8 11s. So this guy is just like that, and this guy is just like that. Okay?
And then we draw one card at a time.
In the first, yes, I'm going to draw one card at a time, and first I'm doing it with replacement. So that makes it exactly analogous to what we did when we rolled dice. Because when we roll dice, you roll the 2 dice and you get some value, which is either 2, 3, 4, and so forth. Now, the same thing happens. You pick a card, you get some value. The values you get are the same numbers, but the probabilities of getting those numbers are different, because now, in fact, for example, the probability of a 7 is 8 over 52 instead of being 6 over 36. Yeah.
So it's going to be a king?
12 would be a point if you rolled, yes. No, excuse me, no. The rules are exactly the same as before. So if I pick out a 12, pick out a queen on the first trial, I lose. Remember, I win on the initial trial if I get 7 or 11. And I lose on the initial trial if I get 2, 3, or 12. And anything else is my point. So the rules are exactly the same. The only difference is that the probabilities that fit in this formula are different. Okay, and what I'm trying to do is I'm trying to contrast sampling with replacement, in which a roll of the dice is the same as a choice of the cards, because the trials are independent because I put the card back each time. So putting the card back each time I pick one out means that from trial to trial, the composition of the deck stays the same, so the probability of pulling out the individual card stays the same. Which is, if I roll dice, everything is the same from trial to trial. They are presumably independent trials. They don't affect each other. On the other hand, if I sample with replacement, that is, without replacement, I keep the card out of the deck, then the composition of the deck changes. The probabilities change. The trials are dependent, and then we want to see how these things compare.
What happens if you roll a 12 at the second trial? Does it still, do you still lose?
No, it's the same thing as with regular craps. With regular craps, once you get past the initial trial, the only thing that matters is point or 7. If you get your point, you win. If you get your 7, you lose. And if you get anything else, including a 12, the game is just repeated. So the rules are exactly the same, only the probabilities change. And the difference between the two cases, A and B, is that if I'm sampling with replacement, it's exactly analogous to dice because they are independent trials. But if I'm sampling without replacement, then it's not exactly analogous because, as we already know from the earn problem, the trials are dependent because each time I deal out a card, that's going to, and I observe it, that's going to affect the probabilities associated with the remaining cards because there's one less card in the deck. Okay, so what's the probability of winning if I sample with replacement? So it's the same formula as before, and everything is the same interpretation as before. The only difference is that the probabilities are different. Okay, so when I'm using the cards, the probability that I get any of these numbers, 4, 5, 6, 8, 9, or 10, is 4 over 52 because there are 4 4s, 4 5s, 4 6s, and so forth. So in this sum, each of those terms is going to be 4 over 52. Okay, similarly, for the numerator, the probabilities values are going to be this. For each value of I, the probability is 4 over 52. And for 7, the probability is 8 over 52. Same one over here. So each of these terms is going to be the same. There are 1, 2, 3, 4, 5, 6 of them. So I'll just multiply that by 6. And that's the answer. If you work that out, that turns out to be equal to exactly 6 over 13, which is 0.462. So here's my question. How does sampling with replacement and sampling without replacement, what difference does it make? Does it make a difference whether I take the card that I got and put it back in the deck, or can I just continue to deal them out? The 4 over 52 is, remember that instead of rolling the dice, I'm going to pick a card. For each denomination, there are 4. There are 4 aces in the deck. There are 4 2s, 4 3s, 4 4. It's an 8 because I'm counting the aces as 7s in order to make the numbers that I get from the deck consistent with the numbers I get when I roll the dice. So the random variable values are the same, but the probabilities are different. Okay, so remember that whenever you have a sample space, there are 2 pieces that are important. One is, what are the events that can happen? In this case, what are the values you can get when you roll the dice or pull out a card? And then the second is, for those events, what are the probabilities of those events? And that's They can be assigned in any way such that those numbers are non-negative and add up to 1. So the recognition here is that card craps and dice are almost identical, at least if I'm sampling with replacement, except that the probabilities that actually fit in the formula are different, but in fact they're easier than they are with dice. No big deal at all. All you got to do is recognize it's the same problem. And this is what the answer turns out to be. So now I want to do the same problem if I'm sampling without replacement, which is the natural way to do it if you're using cards. So I take the deck, I shuffle it, and then I deal out the first card. That's the X0 roll. And then if the game is not ended, I deal out the second card, and then the third card, and so forth. Yeah?
Can one consider the fact that you roll a pair of dice as sampling with replacement?
Yes, rolling the dice is the same as sampling with replacement in the sense that every trial is statistically the same as every other trial. The trials are independent. This is the point I'm trying to make. Now, if I sample from the deck, if I sample from the deck with replacement, obviously each trial is independent of each other trial. If I roll the dice, obviously each trial is independent of each other trial. Now, when I say obviously, it's really not that obvious at all because we're assuming that nature works in a certain way. It's the only reasonable assumption to make, but it could be that somehow or other the trials are dependent because the dice might be connected to each other by some kind of magnetic field, or who knows. God could be controlling it and making it work out the way she wants to. We don't know that. But as scientists without any other information, what we assume is that whenever you roll the dice, whatever happens on any trial is, from a statistical point of view, exactly the same as any other trial. The only difference from one trial to the other is randomness. On the other hand, with the cards, if you put the card back in the deck each time, then it's analogous to the dice, because each time I draw a card out of the deck, the experiment is the same as it was for the previous case, as long as I shuffle the deck, which we're assuming. But if I sample without replacement, then once I remove the card from the deck, that means that the deck has one less card in it, and so that card cannot appear again. Also, if I sample with replacement, just like with dice, the game can go on forever. There's no necessary maximum number of rolls before the game must end. But if I play with a deck of cards, then obviously I can only deal out 52 times. So at most, the game is going to go 52 times, because it's got to go less than that. Okay, so here's the question then. The question is, I want to compare the probability of winning if I sample with replacement against the probability of winning if I sample without replacement. So we'll take the usual vote. Because I'm not trying to trick you here. I'm just trying to see if you understand things. So what are the possibilities? It could be better to sample with replacement. In other words, the probability of winning if I put the card back could be better than if I don't put it back. Or it could be worse, or they could be the same. It might not make any difference in terms of the probabilities. So I want you to use your intuition and try and make a guess as to which one you think is right. Okay, so think about it a minute, because you can't think too long because we're using expensive airtime here. Okay, how many people think that the player has a better chance of winning if he puts the card back in the deck than if he doesn't? How many vote for this? 1, 2, 3, 3. Okay, how many people think that it's the other way around? 1, 2, 3, 4. How many people think it doesn't make any difference? Okay, that's everybody else. I'll say, I don't know, 12, roughly. Okay, so I know why people guess this. They guess this because in previous cases, that's the way it's turned out to be, right?
Right.
That's a reasonable argument, but it's going to turn out to be not true. So, for the people who guess this is the correct answer, as we'll see shortly. So, can somebody explain to me who made this guess what the argument was, why it's better to sample with replacement than to sample without? What was that?
With replacement, you have an infinite sample space, basically, with the other one in small samples, which when you got you tries, so you narrow down your sequence probability.
You think that the fact that the sample space is infinite rather than finite makes a difference?
I
Okay.
think it's because when you pull one card out, you point. So when you go to do your second subsequent trials, you have fewer possibilities to get a winning card.
Yeah, that's the point.
Yeah.
Okay, so if you're sampling without replacement, and the game, remember the first trial, it doesn't matter whether you're sampling without replacement or not. So whether the game ends on the initial trial is the same in both cases. But now let's suppose that you're sampling without replacement. That means that the card that you've pulled out that's your point, now instead of having on the next trial 4 chances out of 52 of picking that card, you'll have only 3 chances out of 51 because that card has been removed. So therefore, it's less likely that you're going to make your point if you're sampling without replacement, and so therefore the probability of winning should be less. So let's put it in the formula and see that that's what happens. Of course, it shouldn't make a big difference, but it'll make some difference. So the first thing to recognize is it's the same formula. The only thing that's going to matter is that the probabilities in there are going to change. So now I'm going to do, I think I'll write it here. What's the probability of winning under B? The probability that my initial roll is a 7 is exactly the same as before, 8 over 52. And the probability the initial roll is a 11 is the same as before, 8 over 52. Now let's see. Now I've got this same term right here, and for each of these, it's going to turn out that the stuff in here is the same, but it's not that is, I'm going to have 6 terms. So let me write them out. Let's take the first one. Let's take the case where I is equal to 4. What's the probability of rolling a 4 on my initial trial? As before, it's 4 over 52. Okay, now, what's the conditional probability of getting a 4 before I get a 7 if I'm sampling without replacement? Well, 1 4 has already been removed, so that means that from this point on, I have exactly the same statement, except that now these X's don't correspond to a deck of 52 cards, they correspond to a deck of 51 cards with the point removed. So that means that the probability of rolling a 4, once the 4 has been removed, one of the 4s has been removed, is now 3 over 51. So instead of 4 over 52, that term is 3 over 51. Again, instead of 4 over 52, that's 3 over 51. And instead of 8 over 52, that's now 8 over 51. But that's going to be the same whether it's a 4 or a 5 or a 6 and so forth. In every case, these probabilities are all going to be the same numbers. So again, I just have to multiply by 6 and then do the arithmetic. So the arithmetic is going to be slightly different because instead of having 4 over 52 and 8 over 52, I've got 2 over 51 and 8 over 51. When you work out that arithmetic, that will turn out to be exactly 248 divided by 572, which is equal to 0.434, which is slightly less than if I sampled with replacement, or a 0.462. So your intuition is correct. Okay? Okay, so there's a couple of lessons to be learned from this. One being that this was a midterm exam question. But it's not that bad if I tell you in advance what I'm going to do, right? So if I were to say to you, I'm going to look at the craps game after we've just done the craps game in detail, but instead of using dice, I'm going to use cards, and that's the clue, and then you have to think about it. The first thing that come to your mind is, well, how are you going to do that? Maybe I would tell you this deal right here. All right, so let's say I've told you that. The first thing that's supposed to come to your mind is, well, am I sampling with replacement or without replacement? And then, well, does it make any difference or not? And then if I'm sampling with replacement, obviously it's exactly the same as dice, except that these probabilities are slightly different. And if I'm sampling without without replacement, then what? Well, that's the critical question. Now, if you're smart enough to think of that in advance, then you would presumably solve the problem, and then when you took the exam, you would already have it done. If you haven't thought of it in advance, nevertheless, you would have been thinking about it, so it shouldn't be, you shouldn't have to spend time worrying about what the question means. So that's the way these exams go. In other words, if you think about the right things, you're okay. If you think about the wrong things, you're less okay. Okay, so on our exam, let's see, where it stands now is, I think I said this, the sample exam, which is the one from summer, is posted on the website now. So you're supposed to download that and have that ready. That is, do it in advance, and we'll go over that in class on Thursday. And then I'll give you some information about the next exam and go over homework 0. And then that's it. Then following Tuesday, any questions that you have, or we'll start on the next chapter. In fact, I'm going to start on the next chapter now because, well, I got 20 minutes. Unless, of course, there's questions. So any questions about this?
So the midterm's just going to cover through what we just talked about now?
Yes. Midterm will cover through chapter 3, emphasis being on the stuff that we did in class. Same concept, just like this is. These are all the same concepts. But actually, I think it's going to be easier than this. I've tended to start making midterms easier. Because remember, the prime purpose of the midterm is for feedback anyhow. It's not for a grade. So that the grade is not as important as your feeling when you get the midterm back as to whether or not you screwed up because you had no idea what I was talking about, or you screwed up because you just didn't get that problem, or you were nervous or something like that. That's the way you should look at it. Okay, so any questions? Are we ready to go on to the next topic?
Why you got 2, you know? That's why.
Why is it 8 over 52?
Yeah.
Because in card craps, what I'm going to do is I'm going to count as a 7 either a true 7 or an ace. And in a deck of cards, there are 4 7s and 4 aces, so there are 8 cards that I'm going to count as a 7. Same thing with the 11s, because I'm going to count as an 11 either a true 11, that's a jack, or a king. And by doing that, I can map the cards into the dice in terms of the random variable values. The random variable values, then, all I can get are the numbers 2 through 12, which is the same as with the dice. The only difference is that the probabilities for the cards are different than the probabilities for the dice. Probabilities for the cards are actually simpler because all I have to do is count the number of cards of each type in the deck divided by the total number of cards in the deck, and that's the probability for each individual type on a single trial. Yeah?
We have, for part of this, we're doing without replacement, and we have the probability to do it for one throw away.
Right.
Is that just for the second trial? Or is it any trial?
No, that's any trial. Because remember what we showed. We showed in class that even if I'm sampling without replacement, that if I ignore all the events I don't care about, then all that matters is what the probabilities were in the first trial. If you remember, I did an example like this exactly in class, where we had a deck of cards, and we said that we were going to shuffle the deck and deal them out one at a time, and ask for the probability that we got an ace before we got a face. Let me go over that. Ace before face is exactly the same question. Okay, so what we did there is we said, okay, here we shuffle our cards, and there's our deck. And I'm going to now deal out the card one at a time until I get a card that's either ace or face. And I want to know the probability the ace occurs before the face. Okay, let's say it's here. Now the difficulty is that at first you look at it and you say, well, look at all the different things that could happen, and every time I pull out a card, that's going to change the probabilities for the remainder of the deck because I know what I pulled out. But the observation was that if I sampled with replacement, that the formula looked like a conditional probability, and then when I wrote it as a conditional probability, after summing that infinite series, I got exactly the same answer. So therefore, maybe it didn't matter. So then I went back to the card deck and I said, how can I see that answer without having to sum an infinite series? And the argument went like this. It said, well, since I'm going to ignore all of the cards that are not aces or faces, instead of shuffling them, dealing them, and then ignoring them, why don't I just remove them from the deck in the first place? Because I'm going to ignore them when I deal them out. Okay, so they're now removed from the deck, and that means that the only thing that's left in the deck is aces and faces. Well, there are 4 aces, and there are 12 faces, so if that's all there is, the ace will occur before the face if it's the first card in the deck, the remaining deck, and otherwise the face will occur first. So if I'm pulling 1 card out of the deck, what's the probability? And there are 16 cards, and 4 of them are aces, and 12 of them are faces. What's the probability the ace occurs first? Well, it would be 4 over 4 plus 12. Okay, that's what we did in class. This is exactly the same problem.
Just throw away all the ones that we don't care about.
Sure, why not? I mean, as soon as the first card has come out, I can't throw them away until the first card has come out. But as soon as the first card has come out, and the point is, say, 6, then I know that I'm going to take the rest of the cards. There are 51 cards in the deck, and I'm going to ignore all of them except either the 6s or the 7th. 7 is the one by which I lose, 6 is my point. So I take all the cards that are not 6s or 7s, I throw them out, and then I pick 1 card from the deck. If it's a 6, I win. If it's a 7, I lose. Okay, so there's only a small number of principles here. This whole course is 1 or 2 basic principles, but they can be presented in ways that are tricky, and you have to be able to see through the whole thing and see the essence of it. That's the point. Otherwise, there's nothing to the course, because all these problems are solved using basically the same formulas. So I could give you on the first day the 2 or 3 different formulas, and then we could all go home, because they say in any case all you do is apply these formulas. It's not that simple. Of course, this is the easy stuff. Now we're going to start to get to the real probability. Yeah?
Maybe I got the rules of the game wrong, but in the card traps, the probability of B is without replacement, right?
Right.
And that's lower than the probability of winning with replacement.
Right. With replacement is 0.46, without is
So you got a
0.49.
higher chance with replacement?
Right. The reason being that if you're sampling with replacement, if the game doesn't end on the initial trial, that means that the card you've pulled out is your point. If you're sampling with replacement, you put that back in the deck, and the next trial, there's a chance of 4 over 52 that you will pick that card out, and then you win. But if you're sampling without replacement, you can't pick out that card. You can only pick out one of the other cards of the same number, and there are 3 of those.
And what's the object of that?
Object of craps is to win. The object is, let's go over this at the beginning. Doesn't matter whether you're talking about cards or dice now. The initial roll, you get some value. If that value is 2, 3, or 12, you lose. Game's over. If it's 7 or 11, you win. Game's also over, but you won. If it's anything else, which means if it's 4, 5, 6, 8, 9, or 10, that's called your point. Then you play the game over and over again until either you get your point or you get a 7. If the point occurs first, you win. If the 7 occurs first, you lose. Now, with dice, what you do is you reduce everything to a statement that has in it only the probabilities. It's exactly the statement right here. Only the probabilities associated with an initial roll. Because what we showed is that if you look at rolling the dice continually, that the probability that one occurs before another is the probability of a sequence, which gets longer and longer. And then if the events are independent, then that sequence factors. Let me do it. I still have 13 minutes. Better to do that than to start a new topic. This is what's done in the book. we've got this sample space, and we've got a partition into events A, B, and C. What we're doing is we're saying that we're only concerned with two of these, and the C is everything else. And we want to find the probability that if we sample continually, what's the probability that A will occur before B? Okay. So probability of A before B. So in the first trial, I can get an A before B if the first time I get it, first time I conduct the experiment, is I get A. Or, on the first trial, I could get C and then A. I can't get B, because if I got B, then I wouldn't have gotten A before B. Or, I could get C, C, and A. Or, I could get C, 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 and A, and so on. So there's an infinite number of terms in this series because there's no maximum number of trials before the game ends. And now comes the big step. Now the step is independent trials. This is my usual assumption. So if I'm talking about dice, it seems obvious that that's true. Okay, so for independent trials, this would be the probability of A plus the probability of C times the probability of A, plus the probability of C times the probability of C times the probability of A, and so forth. So the independence is what says that the probability of a string is the product of the probabilities of the individual trials. And that reduces everything to a statement about a single trial. Because now I sum this series, I take out the probability of A, and I'm left with 1 plus probability of C plus probability of C squared, and so on. And now I just recognize this as the formula for the geometric series, or the geometric series for which I use that formula. So this becomes 1 over 1 minus the probability, or the thing that I'm raising to a power. So it's 1 over 1 minus the probability of C. That's the probability of A times 1 over. Now, since A, B, and C constitute a partition of the sample space, then the probability of C is equal to 1 minus the probability of A or B. So I replace 1 minus the probability of C by the probability of A or B, and that's our answer. Okay, so everything has been reduced to the probabilities associated with a single trial. Probability of A plus probability of B. But then comes the observation that suppose I had asked this question. Suppose I had said, what's the probability of A, given that the answer has to be either A or B? Because if it isn't, I'm simply going to ignore it. I'm going to throw those trials away and do it again. So if I just look at it this way, working directly from the definition of conditional probability, I get this answer. And I say, wait a minute, this is exactly the same as that. So therefore, it shouldn't matter, because in this case I didn't say anything about the trials being independent or being statistically identical. All I said was that I'm going to do this over and over again, and I'm going to ignore everything that I don't like. So if I do that, then this ought to be the answer. So then to answer that question, we looked at the card problem. And then for the card problem, it was easy because you could see exactly what's going on. And we saw that we got the same answer whether we used the formula or whether we just took the cards that we were going to ignore and put them out of the deck. And that brings you to the point, to the conclusion that, well, obviously it doesn't make any difference. This is a more general argument than this is. And I don't need the independent trials, which is a strong assumption. So this is the insight. Because if you don't have this insight, if you don't emphasize these aspects of the subject is trivial. There's nothing left, because every problem is once you get to tossing a coin or picking some cards, that's the end of it. There's nothing left. But in real life, these are really the important issues. The questions are things independent? What difference does it make? And furthermore, this is the high school version because there's no mathematics in this. Remember, all we're doing is pre-calculus kind of stuff. There's no integrals, no derivatives, none of that stuff. Now we're going to talk about, or soon, we're going to talk about cases where the outcomes are not countable. That is, we're going to go from discrete probability to continuous probability, or from discrete math to continuous math. So, to give some ideas to that, why it's different, why things are going to get more difficult now. Suppose we go back to this original question we looked at a long time ago, where we have this spinner, and you flick it and you pick out a number between 0 and 1. And I ask for the probability that I pick out any particular number, that it lands any particular place. Well, how many numbers are there between 0 and 1? If I don't want to make this line discrete and arbitrarily say that I divide this into a finite number of intervals, then there's an uncountably infinite number of numbers between 0 and 1. So the probability that I pick out any one of them, what's that going to be? The simplest model is to say, well, there's no reason why this arrow should pick out any particular number, why it should tend to lie in the middle or towards the end. If I'm simply spinning this dial, every point ought to be equally likely. So I have an equally likely probability distribution. In other words, I have an infinite number of possible outcomes. Each outcome must have the same probability, and they must add up to 1. Well, how can that happen? That's impossible. Because if all the probabilities are some positive number, no matter how small, if I multiply that by infinity, it's going to be greater than 1. It's going to be infinite. So I have to talk about probabilities from the viewpoint of calculus, in the same sense that if I want to calculate an area under a curve, okay, what do? Well, what I do is I divide up the area into little strips, and I calculate the probability associated with each strip, and then I take the limit as the number of strips goes to infinity, the width of the strips goes to 0. So what I'm adding up is I'm adding up an infinite number of infinitesimal areas. But as you all know, in the limit you get exactly the correct result. And the fundamental theorem of calculus says that, okay, it's intuitive that if I add up an infinite number of these infinitesimal strips, I am going to get the area. Because all I'm doing is making my original area more accurate as I take the measurements finer and finer. But I can't actually take them in the limit and add them up by hand because there's an infinite number of them, and each one of them has width 0. So the fundamental theorem of calculus is, in a sense, a trick that tells you how to do that, how to actually calculate this limit, and that's a big deal. But the trouble is that most freshmen don't understand it. They simply learn how to do it. And that's part of the reason that people had so much problem with homework 0, because homework 0 simply asks you to calculate an integral recognizing that it's an area, and people seem to have trouble with that. They can only do hard integrals, where there's some trick to it, rather than easy ones, where the area is just a geometric figure. In any event, what I do here in calculus is I add up an infinite number of infinitesimal areas, and I get the non-zero finite area under the curve. So similarly, I'm going to want to apply this argument here so that the probability of each individual value will be essentially 0. In fact, it will be 0. That's the thing that people have a lot of trouble with. If x is the value that the arrow points to, the probability that x is equal to any particular value t is 0. Because I have an infinite number of them. Remember, this probability is like one of these strips. But if I added up all those zeros, I would get 1 if they're probabilities. Of course, you don't add these infinitesimal values. You integrate. You take the pass from the limit, you pass to the limit from a sum to an integral. So probability becomes college level, let's say, It uses calculus when we start asking questions about random variable values that can take their values in a continuum rather than in a countable, discrete countable set. Okay, so that's where the calculus is going to come in. That's why it's a prerequisite for the course. However, you don't have to know lots of tricks of calculus. You just have to understand this idea of a limiting argument and what an integral is. So if you can do homework 0, that's all you need to know to be able to handle the rest of the course in terms of mathematics. Okay, we got about 3 minutes left. Any questions? Yes? I've graded it, but I don't want to give it back because, remember, there are feeds people, and they're a week behind. So I don't want to make the solution on the board here, and then, of course, all the feeds people will simply see the solution. Well, they wouldn't do that, I know, but I don't want to give them that opportunity.
Do you post grades, or is there a way to track the grades?
I'll hand it back on Thursday, and I'll go over it in class. Okay? Okay, see you on Thursday.